Through valence shell electron pair repulsion theory, we can figure out the electron pair geometry of a compound because the number of electron pairs around an atom will tell us about the spatial orientation of these domains. But if the central atom of a molecule has lone pairs, we will also need to know about its molecular structure, which will be different from the electron pair geometry because it includes only the placement of the atoms rather than both atoms and lone pairs. If a molecule has no lone pairs, such as methane, then the electron pair geometry and the molecular structure will be the same, since all of the electron pairs are covalent bonds that lead to other atoms. We know that this molecule will be tetrahedral, and the way we represent this three-dimensional molecule in 2 dimensions is with dash and wedge bonds. When we use this notation, the wedge bond implies that the atom is coming towards you, or is closer to you than the plane of the page or the screen. And the dashed bond implies that the atom is going away from you, or is farther away than the plane of the page or the screen. If we look at other molecules that have tetrahedral electron pair geometry, we can see that the molecular structure will begin to change as we replace atoms with lone pairs, because the molecular structure is only concerned with the locations of atoms, not lone pairs. Look at ammonia, for example. Nitrogen has 3 bonds to hydrogen atoms and 1 lone pair. That's 4 electron domains, so ammonia has tetrahedral electron pair geometry. But the lone pair is not included in the molecular structure. We give this molecule a different name when it comes to the molecular structure. We will call it trigonal pyramidal. Let's compare methane and ammonia in order to see that there are similarities in the orientation, as they have roughly the same bond angles, but they certainly have different shapes because of the differing numbers of atoms. We could do the same for a water molecule, which has 2 bonds and 2 lone pairs around the atom. That means it has 4 electron domains and will have tetrahedral electron pair geometry. But with 2 lone pairs, we will call the molecular structure bent. The bond angles decrease as more lone pairs are added because lone pairs repel other electron density slightly more than bonding pairs, as we can see here for ammonia that has bond angles that are slightly different from those of methane. This table will show us all of the molecular structures that are possible within a particular electron pair geometry as we successively replace atoms with lone pairs. The more electron domains there are, the more possible molecular structures there are, because there are more combinations of atoms and lone pairs possible. We should also note, for most geometries, each position is identical, but for trigonal bipyramidal compounds, there will be axial and equatorial positions that are not the same, given the combination of 90-degree and 120-degree bond angles, sort of like a trigonal planar geometry and linear geometry combined. In this geometry, lone pairs will occupy equatorial positions.